Hello, everyone. My name is Song Zhang, a senior solution architect at AWS Energy and Utilities. So I'm leading the utility solutions for HPC on AWS. In this presentation, I will show you why and how you should proceed with AWS to implement a scalable, resilient, and sustainable HPC solution. So I will start with reviewing the business needs for HPC, then touch your pain points of using an on-premise cluster, and I will show you a multifunctional application agnostic HPC platform architected on AWS. Finally, I will wrap it up with a run example and a demo. So the business drivers for HPC is very straightforward. We all know that our grid is quickly penetrated by distributed, heterogeneous, renewable resources. The existence of these inverter-based resources has been changing the way how we plan and operate the grid. The number of the grid simulation scenarios that need to be studied is now rocketing up. Power system engineers rely on their personal laptops and on-premise workstations or clusters to run the large-scale grid simulations. Those simulations are usually considered as non-time critical. However, these simulations sometimes are compute intensive and very time consuming. For example, running Monte Carlo simulations to determine the resource adequacy or running the time domain simulations to probe the grid stability limits. Sometimes it can easily take hours or even days to complete a multi-time point simulation case. And for the time constraint studies, in a shorter time horizon, such as operation planning or the forward capacity market, the status quo is not all scenarios are usually considered for study. Engineers have to use a screening approach or cherry-picking method to select the important scenarios for analysis. As a result, the simulation outcomes are not quite credible because there is a lack of the full study of all possibilities. So if you have ever run simulations on an on-premise HPC before, these pain points will not be a surprise to you. First, on-premise HPC cluster usually has a poor elasticity because it is not designed to scale easily. Adding new nodes to the cluster may take up to a few months due to a long and tedious procurement process and the project lead time. And it's almost impossible to predict the demand for computing resources, although it is statically increasing, but sometimes it may encounter spikes from time to time. So it is very challenging to provision the resources for computing and storage accordingly to meet such demands. And certainly, HPC clusters are usually in the siloed environment because they are heavily customized and controlled, make it very difficult to integrate it with other functionalities such as machine learning, data analytics, ETL jobs, and etc. And finally, our IT folks might find maintaining aging hardware and upgrading, patching the software on HPC is a headache for them. So they're trying their best to avoid, managing a on-premise HPC as possible as they can. As I experienced HPC need for utilities who worked closely with power system engineers, I summarized these key features that are needed on an HPC for engineering study, regardless of where it is hosted. So the first needed feature for running utility analysis with HPC is the platform needs to be elastic enough. It is not only need to scale out to meet the varying demand, the bursting demand for the grid simulations, but it should be also able to scale in to protect the resources from being wasted. So the second needed feature is to meet the very unique requirement in the power industry, because most of the power system software applications only have Windows distributions. So the HPC solution has to support the Windows computing environment, unlike many other HPC solutions that only rely on the Linux workload. And the third feature indicates that the cluster should be able to allow multiple users to submit their jobs asynchronously and allocate the resources dynamically to different jobs. So the cluster has a high utilization rate. Absolutely, there should be also a priority queue to execute jobs of different importance. The higher a job urgency has, the sooner it should be executed. And another feature needed by the platform is it should be secure enough. And even though utility analysis do not always involve the BCSI data, it is always a best practice to encrypt the data and the rest in transit and in use by using the most robust and strongest encryption method. And the solution also needs to be cost effective to help our customers save money compared to the total cost of ownership by owning an on-premise HPC. So if this diagram shows you a Windows-based HPC cluster on AWS, if you are not a solution architect, you don't have to dive deep into each services shown on this diagram and their connectivities between each other. Generally, this design can work compatibly with any Windows-based power system software that can support floating or network licensing. And you can bring your own application license to the cluster here. And the infrastructure as a code user script we provide can help you automate the installation and the configuration of the license manager for you, while the compute nodes are grouped into the auto-scaling groups, whose number can grow or shrink depending on the simulation demand. So there are several key enablers for this HPC solution to meet the grid simulations needs. First one is the EC2 auto-scaling group. It handles the auto-scaling for the worker loads or compute load of a cluster to meet the varying demands for computational needs. And the second one is the HPC Pack, which is a free tool for resource management and job scheduling for Windows applications. And in order for the cluster to manage the loads in a domain, you also need to use a manage the Active Directory on AWS. Helps you to control the domain for HPC cluster. And you also need to use the S3 in this solution for the simulation input data and the output data storage. The advantage of using S3 here is you can get rid of the database maintenance. And another reason is power system software simulations output are mostly file-based. So it matches the S3's characteristics perfectly by using the object-oriented service abbreviated as S3. And additionally, the fine-grained AWS services with over 200 fully featured service can enable the seamless integration of the HPC platform with other needed post-processing functionalities, for example, the ETL, machine learning, and business intelligence. So the essential capability of an elastic computing platform for HPC is its dynamic scaling strategy of the compute load. So this is realized by creating a target tracking scaling algorithm with RAG matrix, including a number of tasks, number of the virtual cores of the processors and of the virtual instance, and job priority, as well as the average task completion time from statistics of the historical runs. So the compute load will be shut down when two conditions are met. First condition is the compute node has been continuously idle for over a specific period of time, for example, 30 minutes. And the second condition is the instance has been running over a threshold, like an hour. Even though you terminate the Windows instance in the middle of an hour, and you will be only billed by the seconds that the instance is running. The reason why you don't want to launch and terminate the instances too often is because there will be warm-up time for software configurations and domain joining. You may want to consider let the running compute loads stand by for a while to process incoming jobs at any time before shutting them down. So this chart shows you that the flow of the job process on the HPC. The users will use a web portal of the HPC pack to submit their jobs from XML file to the head load through their browsers. So they can customize the task's content through Python or PowerShell scripts. So once the job is submitted to the queue, the head node will perform a parametric sweep to iterate each of the tasks in the run. And it will substitute the variables with the concrete values to represent each task and distribute the task across the workloads for execution. And when the simulations are done and the output are written to a specific S3 bucket to store the simulations raw output. So next, I will use an OpenDSS example to illustrate the benefits of such HPC solution on AWS. The reason why I'm using OpenDSS here is because it is open sourced tool which provides the essential functions as other mostly used in industry software for distribution analysis, such as SIME by Eaton and Synergy by DNVGL. So if you look back to the dynamic, the architecture diagram, you can see that we have kept the capabilities to help you set up the licensing managers for the most commonly used software like SIME and PSSE, and how to set them up for the communication between the licensing host and the compute load. Okay, so the simulation we run through OpenDSS is our yearly simulation for the time series power flow. So basically, the simulation runs and the different node profiles, and, and each node shape resolution is and hour interval, and the total points of on a node shape curve is 8,760 points throughout the year. The test case we used is HB 123 bus system. So in this demo, we are going to use a cluster comprised of 2 compute loads and use the instance type for C5X large, which has 4 virtual cores and 8 gigabytes of RAM. So the job completed and 12 minutes on the cluster. If you run this job sequentially on a local machine, it will take you up to 1 hour. So this is a very straightforward comparison between sequential run and parallel run. And the prorated cost for this simulation is 28 cents based on the estimated cost calculation by using the AWS pricing calculator. So you can customize your dashboard by adding the charts to the web portal here. Even though you cannot edit the metrics directly, you can still, by creating this charts to deliver the direct insights into the performance of the cluster, which is running right now. And of course, you can view the job details and the task and subtask level, include the start and end time, and also the job output. And once the simulations are done, you can execute an ETL job to transform the raw output to curated data so you can query them later through AWS Athena. I will stop my presentation here. for the rest of time, let me launch a demo to show you how you should work with AWS HPC for the great simulations. Okay, now let's start the demo with provisioning a HPC cluster through CloudFormation. First of all, let's go to the CloudFormation webpage and click the Create Stack button and upload the YAML file that used to define the HPC workload. And we go to the next page. You will need to specify a bunch of parameters. You need to give a stack name and specify the S3 bucket for installation and the bucket region and the AMI's description name to indicate which Windows image the head node and compute node will use. And you need to specify your side block for the RDP sessions allowed for the user login, and also need to give the domain DNS name and the LED BIOS name, which will be used for the web portal login. And also give the head node and compute node instance type, as well as the number of compute nodes in the EC2 auto scaling group, and the email address for receiving the notifications from the auto scaling group. So after you click the next button, it will proceed to the next page to let you acknowledge the statement. Then you should be able to launch the stack in CloudFormation. Since I already done this previously, you can see I have this stack status shown as create complete. And when we navigate into this stack, go to the output tab, you can see there are some useful links for our navigation. Two web portal URL are given here. So it should be noted that the new web portal currently does support the job submission from the XML file. So we have to use the old web portal for the job submission. So let's open the old web portal first. And before we go to the web page, it should be noted that currently the cluster for the demo purpose only contains two loads. One is a head load, another is a compute load, sitting in the auto scaling group. And the maximum number of the compute node allowed by the auto scaling group is 10, which you can see from the EC2 console here. Okay, so now we have opened this web portal for the job submission. And if we go to the new job command and click the button new job from the XML file, and we can launch the we can submit a job to run the yearly simulations for the OpenDSS simulation. And now you have submitted the job, but it hasn't been kicked off yet. So you need to specify some environment variables for initial estimated time for each task runtime. For example, let's add an environment variable. It loads a little bit slowly today because we're using our small size instance type for the demo. Okay, so now we have added this variable in terms of the key value pairs. So we estimated the task completion time as a half a minute or 30 seconds. So the dynamic scaling algorithm will use this initial estimation to calculate the desired number of compute loads in the auto scaling group initially. Okay, looks like it's not very okay. It's already added. So if we go to the edit tasks, you should be able to see some basic parameters used for the task definition. And you can review the task definition by click um, the message here. So the definition of the task will show you that what is the command you're going to use to submit to the compute load for execution. And because this is a parameter sweep type of task, so it has the start value and the end value to define the number of tasks inside of the job. So currently we have 100 tasks defined corresponding to 100 different load shapes we want to run. So if we click the button submit, that will kick off the job and add it to the queue. If there is a available compute load for execution, the head node will distribute them to the different compute load for execution. And it should be noted that in order to kick off a job, you need to use the AD credentials by retrieving the secret values from the secret manager for the AD account that pre-created for you in the directory service through that CloudFormation. So you can see we have this AD domain created, and it will use this NetBIOS name as the domain name for the AD account. So after you use that secret values to log into the web portal, you should be able to kick off the job. And you can see now I have submitted the job to the head node. And by refreshing the page, you should be able to see that it is progressing. And through the CloudFormation outputs, you can also visit our new HPC web portal by using a different URL. And I already opened it from here. So you can see there is a very nice looking dashboard indicating the load state, whether it is online, whether it is healthy. You can also go to the load tab to view the number of nodes in the cluster. Currently, there is one head node and a compute node for the job execution. And you can also view the jobs similar to what the old portal shows to you. So by clicking the job ID, it will bring you to the job details, providing you the task level information, such as allocated loads, task start time and end time, and the task output. The command line points to the PowerShell script by just varying the case number. And the PowerShell script is the one we use to control the OpenDSS simulation. And you can actually customize it and to control the simulation scenarios you want to run through the OpenDSS. And of course, you can also go to the charts page to add different metrics to this dashboard. For example, I have added 3 of them: the cluster cores, the cluster load, and the cluster jobs. And they are actually refreshed every few minutes to give you the near real-time insights into the performance of the cluster. And you can also go to the logs page to view the cluster level logs. It's very high level information about the cluster. Okay, so once the job is done, you can see the progress is and it's 100%. And you should be able to go to the S3 bucket used for output data storage to view the the simulations output as a raw files. So here the S3 bucket has a prefix output yearly simulation and the case number. And you can see the CSV file are the the output of this OpenDSS simulation to monitor the transformer taps and the 4 different regulators. And you can optionally create some AWS glue jobs to transform the data into other formats, so you can run the queries more efficiently, and then you can link that query results to QuickSight or Grafana to deliver the insights into the data through some dashboards. And of course, you can also grant the SageMaker Notebook instance or Studio to access this S3 bucket, use this data as a training data set for your machine learning model or for other purpose. So yeah, this is about how we use the AWS to create an HPC cluster to expedite your grid simulations, and how can we do some post-processing on top of the data generated by the simulation software. Okay, so this is about the demo. I hope you like it. Thanks for watching.